You're listening to the Thesis Review Podcast. I'm your host, Sean Wellick. I'm a PhD student at New York University, and my research focuses on machine learning, natural language processing, and structured prediction. On the Thesis Review, I'll interview researchers from around the field, centering the conversation around their PhD thesis. In addition to going into the technical content, this will give insight into their history as a researcher, allow us to revisit older ideas, and provide a valuable perspective on how their research and the field itself has evolved since their PhD days. My guest today is Colin Raffel, who is currently a senior research scientist at Google Brain, and soon to be an assistant professor at the University of North Carolina. Colin has worked on a range of fascinating topics, from music generation to generative adversarial networks. Recently, he's been looking into learning from limited labels. His work on the text-to-text transfer transformer, or T5, unified natural language processing tasks into a single framework and consists of a large-scale unsupervised pre-training phase that then allows for adapting to new tasks. Colin did his PhD at Columbia University, advised by Dan Ellis. His PhD thesis is titled Learning-Based Methods for Comparing Sequences with Applications to Audio-to-MIDI Alignment and Matching. It deals with the area of music information retrieval and the problem of matching and aligning audio sequences, which we discuss in depth today. It was also fascinating to hear how this work connects with the wide array of research that he's worked on since. There are links to his thesis and the papers that we mentioned in the show notes if you want more details. And now, Colin Raffel with Learning-Based Methods for Comparing Sequences with Applications to Audio-to-MIDI Alignment and Matching on the Thesis Review. You described your work during your PhD as researching methods to help machines understand music. So what would it mean for a computer to understand music?
Yeah, so during my PhD, especially, I was working in this field called music information retrieval that really encompasses a lot of different subproblems. And the basic goal is that if you have a bunch of music audio on your computer and you want to organize it in some way or analyze it in some way or help someone make music in some way, then the computer needs to understand certain things about music. And I don't have a strong background in musicology or music theory or anything like that. So to me, that mostly means kind of high level things like where are the beats in this song, or what key is this song in, or what chords was the guitarist playing over the course of the song, or can I produce an automatic transcription of the song? And
Mm-hmm.
I don't mean, I mean, there are people in the music information retrieval field who try to study things like, is this song happy or sad, or how will this song make someone feel? And to me, I'm
Mm-hmm.
mostly talking about more mechanical things in terms of
Mm.
how the music was created. And yeah, that's kind of the set of problems that I was interested in, and all of them mostly come down to music analysis. And my personal slant was kind of that if you're making music or you're playing music, then there are a lot of tasks that expert musicians can do that non-expert musicians can't, or that are helpful for a musician to do. For me particularly, I used to DJ a lot, and it was a pretty time-consuming process to, for example, find where all the beats are in a piece of music, which is useful when you're playing a DJ set because you want the songs to transition seamlessly. And so
Mm.
being able to find where the beats happen is super useful for a DJ. And it's surprisingly hard for a lot of music, or at least it was at the time.
So then going back to before your PhD, so you mentioned DJing. Were you interested in music even before being interested in like machine learning or computer science?
Yeah, I would say that the path that I took was that I guess in high school, I started building electronic devices for making music, like guitar pedals and some synthesizers.
Mm.
And I played music. I'm never been a super great musician. I don't have any like accolades or anything like that, but I enjoy playing guitar and making music on my computer. And I ended up making, kind of having like an informal business of building guitar pedals for people, and did that throughout college. where I was studying math. And then after college, I kind of thought, well, if I want to do kind of this more music technology stuff, I should try to get some more formal education in it. And in particular, actually, by the time I finished college, I had done almost no programming of any kind. Like I wasn't a computer science major. And so I sort of figured I'd go do a master's to get more technical skills for doing music technology. And during my master's, I basically learned to write code, mostly in MATLAB, actually, and then and some C++ and Python, but all in the context of basically making music software and analyzing music signals. And then sort of continuing along this rambling path, I ended up doing an internship right after my master's with a company called Imagine Research that was basically trying to apply machine learning to practical problems faced by musicians. One problem they were tackling was if I'm a musician and I'm making music on my computer, or if I'm just a sound artist in general, I might have a bunch of little samples of different pieces of audio, like a different bass drum, people recording a bass drum, people recording a snare drum, different guitar notes being played, and maybe I have this folder with like 10,000 wave files in it, and it's completely unorganized. So how do I automatically tag them? How do I organize them? How do I say like, oh, I have this kick drum recording, find me ones that are similar to it? And to do that, they were using machine learning, and this was back in the days of SV support vector machines. So we were doing all kinds of sort of heuristic feature extraction, and then trying to classify audio and doing clustering and stuff. And that kind of that was actually during that internship where I started to get an introduction to machine learning. And then, as I mentioned, between my master's and my PhD, I worked for 2 years in Pittsburgh, kind of doing independent audio software contracting, and also doing a little research at Carnegie Mellon with Roger Dannenberg. One company that I was working for was basically like a Guitar Hero app that processed actual audio of a person playing guitar. So, it was kind of an educational guitar app. And we used some machine learning there to do pitch extraction. And then I applied for my PhD with Dan Ellis, who was someone who worked at Imagine Research with me when I was interning there. And his lab was basically machine learning for audio signal processing. And I had some strong signal processing background, and I, had been picking up more and more machine learning. And then throughout the course of my PhD, I got more and more interested in machine learning for its own right, not necessarily specifically applied to music and audio, but the whole time applying it back to music information retrieval problems.
Yeah, that's really interesting. So it really started with this, like doing all these various things in music. Machine learning was a tool that you were able to use to keep driving this further. And then eventually you became interested in machine learning itself.
Yeah, exactly. Which I think is, I kind of picked machine learning because it was the most valuable, or it seemed like the most useful tool for attacking the problems that I wanted to, like, for example, music transcription. But then, it's a very interesting field. A lot of exciting things were happening, and I just got wrapped up in the core machine learning research in general.
Mm-hmm. Yeah. And then when you were describing that problem of you have like different drum beats and you want to find similar ones in some database, that's actually starting to sound like what you worked on during your PhD. So did you have like an idea that you wanted to work on these information retrieval type things during your PhD when you started it?
Yeah. So the stuff that I wrote about, and I think this is true of a lot of people, but the stuff that I wrote about in my statement of purpose and for when I applied to the NSF Graduate Research Fellowship Program, the stuff that I wrote about that I wanted to work on was not what I ultimately worked on. I was actually really excited about the problem of, like, let's say you have some audio recording of someone playing a synthesizer, and you want to make that synth sound, and you don't want to just sample the audio. You want your synth to sound like that synth. So you want the filter to be set just right, and the oscillator waveform to be right. I wanted to train machine learning models to automatically do that. And I think people have actually made a ton of progress on this problem, but that's kind of what I was excited about going into my PhD. And then again, like many people, I wouldn't say I floundered around, but I just kind of did some random stuff, kind of looking for interesting problems and learning. I spent a chunk of time learning about sparse coding and dictionary learning, which are super cool and interesting tools, but aren't really things that I ended up using sense. And then at some point, I don't remember when, but I kind of decided, as many people I think were during the time, that the big problem in music information retrieval was just that we didn't have enough training data, enough supervised training data. So everyone wants to be able to automatically transcribe a piece of music, and we had these really tiny training sets because music information retrieval is just very underfunded because it's harder to make money from it or spy on people with it, and so paying a musician to transcribe a piece of music is quite expensive, and so. And at the time, I think I realized or found out that it was very easy to get lots and lots of music scores online. And so I kind of said, well, if there's any way if we can use these musical scores as ground truth audio transcriptions for some corresponding recording of the piece of music, then maybe we would go from having a data set with 100 labeled music transcription examples to like 10,000, and then we'd be just able to solve this problem with machine learning. And the interesting thing, and this actually sort of a theme of my PhD, is that without realizing it, my advisor had actually worked on this problem many years prior. And without telling me, he was a funny advisor because I would suggest some research to him, and he'd be like, "Yeah, that sounds pretty interesting. You should go for it." But not mentioning that like he had a paper from 10 years ago where he like literally did exactly what I was talking about with like whatever the tools were at the time. So he had a paper with one of his PhDs, or actually I don't know if it was a PhD student of his. Anyways, a student of his, maybe an undergrad or a master's student, who basically they were saying, if I have a score and I have an audio file and I want a ground truth transcription, then how do I actually align the two things and get useful data out of those two objects? And ultimately my hope was to create the data set and then train a really amazing music transcription model and solve this huge outstanding problem of music information retrieval. And of course, I only really had time to make the data set, and then I finished my PhD and moved on to other things. But that was the goal, anyways.
Yeah, I see. That's interesting. So the music transcription was like the underlying problem that you really wanted to solve, and then this was even like a large sub problem to solve.
Yeah, exactly. And some people say that music, people talk about AI complete problems. People describe music transcription as MIR complete, music information retrieval complete, in the sense that if you can solve music transcription, then you solve a lot of sub problems like chord extraction, key extraction, beat detection, etc. And so it's kind of like the holy, for many people who work in the field, it's sort of the holy grail. And I felt that no one was making progress on it because there just wasn't enough training data. So I was like, okay, I'm going to make the training data, and then I'm just going to train a big ConvNet, and it's going to totally solve music transcription, and it's going to be a huge deal. But yeah, as you said, this sub problem ended up being big enough for a PhD thesis on its own.
Yeah, a lot of these things sound very familiar.
Yeah.
The floundering around, the advisor working on things that without saying it, and then the sub problems being taking a long time.
Totally.
So maybe let's just for people who haven't maybe seen the thesis yet, let's like talk about what this problem is. So from what I understand, you have a collection of these MIDI files, and then you have a collection of audio files, and you want to both match the MIDI file with the audio file and also align it in time. So align like the different beats and things like this.
Yeah, exactly. And to take even one more step back, a MIDI file is basically just like a score of a piece of music. And at some point, like I said, I realized it was very easy to download tons and tons of MIDI files online. And that's it. I think the reason there are so many of them is because people used to use them for ringtones. So before you could, play an MP3 on a little, clamshell phone or whatever, they had little synths on them, and you could get your MIDI ringtone on your phone, and then like it would play your favorite song, and that was a big deal. And I think that was one of the major drivers of why there are so many MIDI files online. But I think at some point I just scraped a bunch off the internet, and I ended up with like 176,000 MIDI files, which is a lot, right? So if I could get a very small fraction of that as music transcriptions, then like I said, it would be an order of magnitude or two more ground truth data than we had before. And then at the same time, earlier in my lab, actually a student who graduated just before I started, or right around when I started, had made this data set called the Million Song data set that is exactly what it sounds like. It's just a data set of a million songs and a bunch of features and metadata for those songs. And
Mhm.
somewhere on some server, there were MP3 files for them. And in particular, there were these sort of 30-second preview clips that people were sharing with each other, which was not really official part of the data set, but someone had downloaded them at some point and people would share them with each other. So really, I had this giant collection of MIDI files and this giant collection of music audio, and the MIDI files are, they were just scraped off the internet. They had very little useful metadata. It wasn't like, this is Yesterday by the Beatles. It was just like
Mhm.
what information did they put in the file name, and it was often
Mhm.
useless. And on the Million Song dataset side, there was much better metadata, but yeah, there needed to be some way to not only say, okay, I have a MIDI file and I don't know what song it is, so I need to find an entry in the Million Song dataset that matches. And then, like you said, the next step is to actually adjust the timing of the MIDI file to match the timing of the audio recording. Because if you just have a score, it doesn't tell you exactly how the musician played it. Maybe they played it a little more slowly or quickly in different parts or whatever. So you need to
Mhm.
do this matching step and this alignment step in order to get a ground truth transcription.
Yeah, it seemed once I realized there was also this alignment step, it seemed a lot more difficult.
Yeah, yeah. These two steps are actually closely related. In particular, there is this algorithm that existed long before my PhD thesis came along called dynamic time warping that basically specifies a good heuristic for aligning two sequences. And DTW can produce a useful score that basically says, okay, I did the alignment. How well did these things actually match up? But getting the algorithm just right and getting the features right to do the alignment is a little tricky. And then also DTW is pretty expensive. Like it's hard to estimate the computational cost off the top of my head, but aligning an audio file to a MIDI file with dynamic time warping based on their spectrograms, for example, would have just
Mhm.
taken way, 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 way too long if I was going to do the pairwise comparison of every MIDI file to every audio file.
Yeah, yeah. Yeah, you actually wrote in thesis that it was something like 1800 years if you want.
Yeah, yeah. I mean, yeah, that's one of these like funny calculations you can do to just like make your point that like, obviously no one would ever do it like that, but like if you want to motivate, a chapter in your thesis, you can just whip out one of these ridiculous computational time things.
Yeah.
And but yeah, I mean, I guess the big selling point of this thesis is if you believe that it would actually take more than a millennium of compute time, I ended up bringing that compute time down to the order of like 1 week on a 16 core or so CPU. So that was
Mhm.
a win, I would say.
Yeah, I see. And yeah, so maybe before we jump into some more details, just like taking a step back, so this problem of aligning these sequences, again, it at least the way that you wrote it up in the thesis was really nice. It was like, here's the problem I'm going to solve, and then you could see how each part of the thesis was like a stepping stone towards solving it. Do you think that have you used this in other research that you've done, this kind of problem driven approach, or in general, like how do you pick research problems?
Yeah, that's a really good question. I think I'll just say really quickly that I think a lot of people's PhD uh, theses don't necessarily follow this structure. Like, I have one problem I want to solve, and
Mhm.
here is the sequence of steps that I need to take to solve that problem. And I think that's okay. But to me, it was really important personally that I felt like I was writing, this like cohesive document. And so I kind of was always hunting for a problem where I could write a whole thesis about it. Um, and fortunately, I found one that managed to decompose in that way into like four papers that very logically flowed one into the other. Um, and I wouldn't say that at the time I had enough foresight to really know that that was true because like I said, I sort of thought going into it that I would solve the dataset problem in a year in one paper, and
Mhm.
then I would spend the next 3 years or whatever solving music transcription, and that didn't happen. But I would say that in general, most of my favorite problems to work on are of this flavor, where you basically say, I want to solve this problem in some particular domain, or just an outstanding problem in the field. And the tools that we have can't solve it. So first I need to develop the tools, and then I can apply it back to the problem. And then my favorite thing to do, which is a rare thing, but sometimes you can complete the cycle and you can sort of say, okay, now that I've made these new tools, what other problems can I attack with them? And the best case scenario is that you have these generic tools that can be applied, across fields. And, one thing that right after my PhD was done, one thing I was starting to think about was, well, a vaguely similar problem is, on the internet, there are a bunch of documents in, let's say, French and a bunch of documents in English, and some of those documents are translations of one another. If I have a French document, can I find the corresponding English document and then align them? And now I have a ground truth, paired translation for machine translation systems. And, I had this idea without having any familiarity with the field of natural language processing. And of course, people had actually worked on this before with, different tools, and I never actually went down that path, but that's the kind of cycle that I like to try to work on. Because I think grounding the work that you do in a real concrete problem either in some subdomain or just an outstanding problem can really make it have more impact, and also sort of make it clear what you're trying to achieve.
Yeah. And then that's interesting. Like once you develop a solution, so in this case, like comparing these different sequence or subsequences, then you could possibly transfer that to some other domain without even without even knowing much about the domain.
Yeah, I mean, that's the dream. That doesn't always happen that way, but yeah.
Yeah.
And the other thing that sometimes happens is that you try to attack one problem in some domain and it doesn't work. So then you switch to another problem in another domain with the tool that you were building. And that didn't happen in this thesis, but that's happened with some of my other work. Like, for example, we had a paper on a VAE for music sequences, and I was really excited at the time about applying VAEs to text and actually really getting them to work. And we never actually got it working when we were working on that project, but it ended up working super well for music. So it's useful to be able to pivot like that too.
Yeah, and then so in your thesis, there's a whole chapter on these MIDI files. So I actually learned piano on these Roland pianos, which are electronic pianos, and they have MIDI files that play the song, and so it's kind of like an artificial teacher to help you play along with the song, and you could speed up the tempo and all this. So when I saw MIDI, it like brought back all these memories of playing on those pianos. But maybe we could talk a bit about like what this is and then how it's actually represented, because I found it to be kind of surprising that when you actually input this to the model, you're actually using this spectrogram representation.
Yeah.
I was picturing
Totally.
it as being like these discrete tokens or something like that.
Yeah. So, MIDI is interesting. One thing that I didn't appreciate before I started working on all of this stuff is that MIDI files were actually, or MIDI in general, and MIDI files in particular, were actually invented before the internet really existed, like in a widespread usage. So they're really old. It's a really old format, and it you when you buy like a synth today, it still communicates via MIDI to your computer, for example. Like it's still a very common protocol, and in my opinion, it's by no means perfect, but they somehow managed to get it right in some sense, and it has really stuck around. But yeah, what MIDI actually is just it's a protocol. So it basically says, this sequence of bits corresponds to this event, and the event could be, turn a note on at this particular pitch, or change the amount of reverb on this particular instrument, and so it's really just a specification where lots of sort of musically meaningful events are outlined. And it was actually designed as a streaming protocol. So, if I'm like playing notes on my keyboard and I want to send those notes to my drum synthesizer, then how am I going to communicate what buttons I'm pressing on my keyboard, for example? And later, after they made the MIDI protocol, they sort of said, oh, well, we actually could just sort of serialize the list of MIDI events and specify their relative timing. So like, okay, new event that happens, this number of ticks, where a tick is basically a subdivision of a quarter note or whatever. It basically it's a tiny subdivision of the musical meter. And so this amount of time later, do this thing. And then this amount of time later, do this other thing. And yeah, to your point, it is this sort of streaming discrete format, but for the purpose, at least the way that I attack the problem, the easiest way to align an audio recording of a piece of music and a MIDI file was to actually take this sequence of notes and synthesize them. So basically play them back as audio and then compute a spectrogram of them and compute a similar spectrogram of the audio. And then you're basically just aligning two spectrograms. So there's no real like multimodality anymore. And I could imagine a more sophisticated system that kind of included the synthesis step as sort of part of as part of what's learned. But that was definitely the simplest way to at least start attacking the problem. And actually, as I mentioned, my advisor had worked on this problem a little bit, and that's how he had done it. So you take the score and you pretend like it's actually just an audio recording, and then you align them in time. And he had actually worked on a related problem a lot. It was one of his favorite pet problems, which is called cover song detection. So if you have a piece of music that is a cover, like a new band playing the same song, and you want to find other covers or the original song, which is like my favorite thing about this is like I said that music information retrieval research is hard to fund. This is like the hardest to fund MIR problem. But he just like loved cover songs. And it's the same problem, right? It's you once you synthesize the MIDI file, it's basically a bad cover. I mean, it's just a very robotic cover played on relatively poor synthesizers of the original song. So you're basically doing cover song ID. And dynamic time warping of spectrograms was one of the main ways people.
Mm-hmm. I see. You mentioned this music VAE, and I think in that paper you were generating to a MIDI representation, or you were using a MIDI training set. So there's also been some very recent work from like OpenAI on this jukebox model, and they're trying to directly generate audio. So do you think that MIDI is a good representation for generation, or do you think people should like move on to just working on generating audio?
Yeah. So one way to think about what MIDI is that it's a very, very it's basically a compression algorithm with a very, very high compression rate. You can almost think of it as an audio codec. Because if I have a piece of music, like an audio recording of a piece of music, I can represent it as a MIDI file. And the compression ratio goes down from, let's say a 50 megabyte wave file to like a 5 kilobyte MIDI file, which is crazy. But it's a very lossy compression format because you lose all of the specific timbre of all the different instruments and all of the really often you lose the fine-grained timing. But in machine learning or just in general, it's often much more efficient to represent things in a semantically meaningful compressed space, right? Like it's much. If I want to generate 5 minutes of audio, it's much more computationally cheap and probably much easier to learn if I have a format that is, a 10,000x compression that is semantically meaningful. Right. And that's that's to me one useful way of thinking about what MIDI files are. When I was working on my PhD, everyone kind of was starting to think about, what if like instead of using spectrograms, we could process raw audio directly, or what if instead of generating MIDI events, we generated raw audio, but no one had gotten it working really. And I think it wasn't really until the WaveNet paper came out that people really thought that we could generate raw audio waveforms in a reasonably high fidelity way. And MIDI is definitely not the perfect format for generating audio. It's sort of, like I said earlier, it has this awkward sort of streaming event style approach where you don't say like, create a note that starts at 5 seconds, that ends at 6 seconds. You say like create a note and then wait a second and then stop the note. And it can make things get like a little ambiguous in like a technically uninteresting way. But overall, yeah, I mean, if you don't care about generating like really the nuance of music. If you just want to generate this sort of compressed format that is technically music, but doesn't sound like something you'd actually want to listen to when it's synthesized, then MIDI is really great for that. And for music VAE in particular, the goal there was, if I'm a musician, then often I will write down my MIDI files that I want to play, and then later I will control how that MIDI is generated. So I'll tweak my synth parameters, or I will change my drum synthesizer or whatever so that it sounds just like I like it. And you kind of let the human do that part, but you give them a tool that helps them generate sort of the backbone, which is the actual underlying music that's being played.
Mm-hmm. I see. So yeah, like in summary, the compression that MIDI has is kind of a useful format that people have come up with, so that could potentially make the generation problem more tractable, potentially.
Yeah, exactly. Yeah.
Yeah. Just one more question on the generation before we keep moving through the thesis. I just had a higher level question. So with this music VAE and with music in general, um, there's always a lot of talk about hierarchy. And so in the music VAE, I think you built in the hierarchy into the architecture.
Mm-hmm.
And then if we really fast forward a lot and we go to like this T5 model, the text to text model, there it's almost like the most minimal thing. You just have a really generic transformer and there's no notion of hierarchy built in. So I just wanted to get your thoughts on this. Like, do you think that these notions like hierarchy have to be built into models? Or another question would be like, do you think music is different from language in the sense that it could benefit more from this inductive bias?
Yeah. No, I think it really does come down to an inductive bias and kind of, I mean, I don't want to call like one domain easier than another, but certainly,
Mm-hmm.
modeling or generating a raw audio signal is more computationally intensive and arguably harder to learn than generating, a sentence or a paragraph, just because of the sheer scale, and there's correlations, at the sample level and then at like a 10 times that level and 100 times that level, where if you hard code in the hierarchy, it just helps your model find a good solution. And in music VAE, we were modeling MIDI or a format that's similar to MIDI, which should make things easier, but it was a VAE of sequences. And so you end up with this difficult problem of posterior collapse, where basically the model ignores the latent variable that you're trying so hard to learn meaningfully, because you want to
Mm-hmm.
manipulate the latent variable and have it manipulate the original data in a meaningful way. And so in that case, that actually made it very useful to sort of manually inject hierarchy so that we could model sequences that were much longer than, let's say a couple, like 100 steps or something like that.
Mm-hmm.
I personally am a big fan of inductive biases in learning, and I am personally amazed at how well the transformer architecture, for example, works at modeling text. But in terms of inductive biases, it's kind of like you said. It has very few assumptions in it. The basic assumption is that every entry of my sequence can affect every other entry in the sequence, and I don't know how, and you have to decide. And it's amazing that that works, but it's probably not the most computationally efficient or efficient in terms of data efficiency, like learning, how to solve the problem and how many labeled examples I need, or how much training in general I need first. But it is very exciting that we have this recipe where we can basically, just throw tons and tons of unlabeled data at the model, and it learns to do meaningful skills, so to speak, and it learns a bunch, sort of internalizes a bunch of knowledge that's then useful for downstream tasks. But if, for example, we want to be able to take a transformer style model and train it on 100 labeled examples and expect that to work, I think that we need a lot more inductive biases if we're not going to do any pre-training or anything like that.
I see. Yeah. So it could be a way of training with fewer labels, and then it could also vary by domain.
Yeah,
Even.
sure,
Yeah.
exactly, and maybe making things more computationally cheap too. And actually, right after my thesis, the problem that I was most excited by when I started at Google Brain was trying to train models to learn this sort of hierarchy on their own. And I made a little bit of progress on that, and then, sort of as I mentioned earlier with pivoting, pivoted towards online attention mechanisms, which were sort of a related problem mathematically, but I got working much better, and so I worked on that for a while instead.
I see. Okay. Yeah, and so then I guess continuing on the journey through the thesis. So I guess now we could talk about how the overall solution that you came up with was structured. So it's kind of these three parts. So you mentioned the dynamic time warping,
Mm-hmm.
and then there's two different neural models. And I think at the end you call it this cascade type model. Um, so first, is that a fair characterization? And then second, I was wondering, like, did you design this cascade idea up front, or was it like you solved the first part and then saw that the next part of the cascade was necessary and so on?
Yeah, exactly. It's your questions that you've led exactly into the correct answers, which are that yeah, you've described it correctly, and the paper presents it in sort of backwards order from the most fine-grained step and most accurate step to the least fine-grained and least accurate step, and that's sort of the order that I developed these methods, because first you say, okay, if we want to align the MIDI file to the audio file, we just use dynamic time warping. It works pretty well. We get a good confidence score at it. And then you're like, oh, this is way too expensive if we want to take every MIDI file and try to match it to every possible audio file. So the first idea was, okay, let's just like make dynamic time warping more efficient. And so what makes DTW expensive? It's that you basically have to compare, you basically do this quadratic dynamic program. And it's quadratic in the input and output sequence length. So if you can make the input and output sequence length shorter, and if you can make the individual comparison between different sequence elements cheaper, then you can cut down the computational cost a lot. And so, like you said, basically what we ended up doing was training a model that mapped spectrograms to these much shorter sequences of binary vectors. And so binary vectors, it turns out, can be compared super efficiently. Most computers have this operation called population count and another operation called exclusivor, which is less esoteric. And when you combine an exclusivor with a population count, these are like machine instruction level in terms of efficiency, you can compute the distance between two vectors in binary space. And so if you can get a sequence of binary vectors, it's much cheaper to compare the individual elements than doing like Euclidean distance in continuous space. And then that worked pretty well, but was still much too expensive. So the next idea was, okay, instead of doing this quadratic thing, let's actually just try to take the whole song, and summarize it as a single vector. This is like you can't cram the meaning of a whole sentence into a single vector thing, like in the music case. And actually, when I told my advisor that I wanted to try this, he was like, oh, that'll never work. And it didn't work that well, but it was totally helpful. And at the time, people, I think, still weren't totally comfortable with the idea that you could summarize a sequence with a lot of information into a distributed representation, into a continuous fixed length vector representation. And the way that I attacked that problem was basically by coming up with what I call a feed-forward attention mechanism, which the easiest way to think of it is that basically I'm going to average my sequence, and the average is the individual weights of each entry in this weighted average is going to be computed by a little attention head. And so then basically each step of this cascade resulted in less accuracy but more efficiency. So the first step you would use to discard most of the possible matches, but you would do it many times faster. And then the second step, you would take the possible matches that were left and you discard most of those. And then at the final step, I don't actually remember. I was trying to skim through my thesis to remember some of these exact numbers. But I think in the final step, each MIDI file is compared to like 100 candidate audio files with dynamic time warping on like the raw spectrograms. And that sort of cascade, people call this pruning when you're doing database search. You're pruning out most of the entries of the database at each step. And by doing these multiple pruning steps, like I said earlier, it made it possible to do this entire 100,000+ MIDI file to a million-ish song pairwise matching in on the order of like a week on this one single desktop computer that I had access to during my PhD.
Yeah, so both of these models that you mentioned were neural models, and you mentioned that like this idea of cramming everything into a vector at the time was sort of a new idea, maybe. I just wanted to ask, like from a historical perspective, at the time when you were developing these things, how prevalent were neural methods?
Yeah, yeah, I love this question. So you know, AlexNet was like 2012, I think, right? And I
Mhm.
started my thesis in 2012, and some of the sort of like deep neural networks or um, deep belief networks for speech recognition stuff was happening just like when I started my PhD thesis, basically. And for I did my PhD at Columbia, and just sort of by coincidence, there wasn't really there weren't really any professors who were taking this stuff very seriously. It was very much like a kernel methods crowd, and even like a learning theory crowd, or yeah, and so I didn't take any classes really where they taught me about neural networks. The only exception was in my speech recognition class. There was like one lecture where the professor was like, "Oh, by the way, recently people found that these deep belief networks work really well. So here's what a deep belief network is." And everyone's like, "What the hell is this? This is so weird." And then like 1 or 2 years later, people were like, "Oh yeah, that whole like deep belief network pre-training thing. We don't have to do that. We can just like train with SGD and it works fine if we have enough data." Um, but kind of the way that I actually fell into the neural model stuff was there was a postdoc in my lab, Brian McPhee, who's actually a professor at NYU now. He's totally awesome, and he I wouldn't say that he was like a I mean, he was super skeptical of deep learning in general during his postdoc, but at some point he was like, yeah, there's this really cool software library called Theano that kind of like builds a computational graph and then compiles it onto your GPU for you. So it makes like GPU programming way easier. And I was like, oh, that's cool. And I was like poking around on the Theano site, and they had these like deep learning tutorials. And I started going through the deep learning tutorials, which like in retrospect, some of them are super useful because it's like, what is a convnet? And then others are like, what is a stack denoising autoencoder? And of course, you like learn all of this stuff as you go through the tutorials. And then also the other influential thing that happened was as I was learning about this stuff, Brian also pointed me to this paper called I think it's called multimodal similarity preserving hashing. And that paper basically said, hey, if I have two objects which are expensive to compare, I can train a neural network to output hashes, like binary vectors, and the binary vectors are cheap to compare. And that sort of motivated me to try this binary vector sequence thing that was the sort of second stage of the cascade. And yeah, in the meantime, like I said, there weren't really many labs or professors who were focusing on neural models. And so one thing I did that was super helpful that I recommend to anyone who's in a similar situation, I just sort of started a reading group in a seminar series. And we would sort of read papers and talk about them. And there were enough people who were kind of interested in deep learning that they came. And then the funny thing about academia is that a lot of times if you ask someone to come give a talk, they'll just come do it. And I remember that's how I actually met your advisor, Cho. I just emailed him when he was joining NYU, and I was like, hey, I have this seminar series. Do you want to come give a talk? And he came and gave a talk, and he was great. And I that taught me a lot too. But yeah, I over the course of my PhD, I would say people went from like super skeptical of this stuff to, it is like basically taking over by like 2016. And yeah, I remember I went to this, I think it was in 2016, where I went to ICASP, which is the big signal processing conference. And I was staying at a hostel because I was a PhD student, and, it was cheap. And there were like 4 people in the room. It was myself, Brian McPhee, and this like random researcher. And this guy just like hated deep learning. And he just was he was like, oh, you guys work on machine learning? And he just like went off on like how stupid deep learning was. He said that everyone treated whatever Jeff Hinton said as like the holy gospel, and it's like none of this stuff is going to work and blah, 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 blah. And that was in 2016. And sometimes I think back on like, what is this guy doing now? Because either he's still like that and he's just like really taking his stand really hard, or like at some point he had to like look deep inside and just be like, this stuff actually kind of works pretty well. Maybe I should start working on that too. But yeah, it was a funny time.
Publicizing deep learning and teaching courses on it now.
Yeah, exactly. Yeah, and actually I remember when I presented one of the paper in my thesis about the downsampled hash sequence stuff at a conference, I haven't gotten very many like adversarial questions when I do conference presentations, but this guy got up and he was like he basically was like, you should have tried something simpler first, which I did, but he was like, you should have tried something. Somebody intentionally called it a convoluted neural network instead of a convolutional neural network. So people were like definitely hating on it. And actually, the woman who's now my wife, but at the time my girlfriend, made me this belt buckle that actually there's a photo of in my thesis that is like a little neural network diagram. And I remember when she made it for me, I was like, oh, this is so awesome, because she'd seen like me using these diagrams. She's like, oh, this is so awesome. But like, actually, if some people saw this, they would like kind of think that it's not like they would take offense to it, but they like don't agree with it, or they think that it's like not good or something. And it's sort of hard to explain. But yeah, it's funny the like changing politics of the field.
Yeah, I actually saw the belt buckle. I was going to ask you about that, so that's funny.
Yeah, she just
brought it up.
Outstanding gift giver, and she just saw, like actually for the reading group, I just had one of these big like old school neural network diagrams where you have the circle nodes and like all of the lines connecting every layer, and she saw that and had one of her friends make this. I'm wearing it right now, actually, this metal belt buckle that, yeah. It's an excellent gift. So, and I figured, I should just like throw it in my thesis because I don't want to have to draw this diagram again. And then it's kind of funny if anyone ever looks at this document, they'll see it and like maybe get a kick out of it.
So then, so I guess though at some point, I guess there was maybe enough results coming out that you became convinced enough that this was going to work, because it is kind of a decision to commit to this as the method that you're going to use, especially when people are telling you that it's kind of crazy.
Yeah. So for me, actually, the moment came because Brian had pointed me to the similarity preserving hashing paper. And I was, like I said, I was learning some deep learning stuff. And there was, I think, as in many downstream domains, there were a couple of people in MIR, in music information retrieval, who were like, hey, everyone, deep learning is the path forward. And then there were people who were like, no. And for MIR, it was like, no, signal processing, like kernel methods, et cetera, like, hand design features, et cetera. And then there were like, 3 or 4 people who were really vocal about deep learning early on. And I was kind of like curious to see whether they were right and, learning all of this stuff. And I basically built the similarity preserving hashing model in Theano and trained it on some spectrograms. And it like, I can vividly remember the day that like, it just started outputting these like binary sequences that respected similarity, and I was just like, oh my god, it's actually doing it. Like it's like, obviously machine learning, it's like, oh, it's doing it all on its own, but this is a pretty complicated problem, and it just kind of started working. And at that point I was like, well, if this is going to work, I should just kind of dig into this. And yeah, I mean, one just like other quick funny historical note was that, like I said earlier, I did all of the work in my PhD on a single desktop machine. And, at the time, no one had GPUs because none of the methods that people were using for machine learning were GPU intensive, So I had to go to my PhD advisor and basically be like, hey, like I want to do these like neural network things with Theano, but I need a machine with a GPU. And so here's like a gaming machine that you can buy me with like a 780 Ti in it. That will let me do my research. And fortunately, he bought it for me. But throughout my whole thesis, I had this one like gaming machine with a single 780 in it. And so everything in my thesis was basically designed around being able to run stuff on this machine. And I remember like, for processing sequences at the time, it was like, oh, you should totally use a recurrent neural network. But it was just way too expensive to use an RNN on these long sequences on a single GPU. And so that's actually where the sequence embedding stuff came from, because one way to get a sequence embedding is to like stick the whole sequence through an RNN and then use the final hidden state or whatever. But that was just way too expensive.
Mm-hmm.
So I was like, okay, how can we parallelize this to make it much cheaper? And that led to this like quote feed forward attention mechanism, just because it's way, way, way cheaper to do things that way. So sometimes, like working within constraints can force you to come up with things that are maybe a little more creative. Although I'm not going to act like, working with constraints is like the most fun thing.
Yeah, that's really interesting though. Yeah, so move from the RNN to the feed forward network.
Yeah.
So that it could fit on your GPU.
Exactly. Yeah.
So now that there's been some developments in deep learning, and knowing what you know now, do you think that you could go? I don't know if you necessarily would, but do you think you could go back and solve this in maybe a more end-to-end way? So, for instance, like given some pair of spectrograms, like directly find the alignment or something like that.
Yeah, totally. I mean, there was definitely a time when I was working on this where I was like, this whole thing where I'm, basically in order to train the downsampled hash sequence thing, these shorter binary vector sequences, I was basically pre-aligning MIDI and audio files that I knew were matches, and then training the model to make the hash sequences similar for those two audio and MIDI pair. But yeah, it would be much better to do it end to end, where you just say like, oh, I want you to learn a good DTW. I want you to learn a good alignment procedure. And I mean, I remember at the time I was like, maybe I should try to spend, like a couple months or a year figuring out if I can stick DTW inside of a neural network. And I just didn't, because what I had seemed to work okay, and it ended up working well enough to sort of solve the problem. But yeah, I mean, there's many reasons why that's a good idea. And actually, there have been a number of papers now that, like, there's a soft DTW paper which basically has a softened approximation of dynamic time warping that you can train end to end, and not only because I think the matching would work better, but also that DTW is not like the correct way to align these sequences. It's just a heuristic that like happens to work pretty well. And so to learn a better policy for that, and to learn the feature representation through the alignment procedure as opposed to as a sort of pre-alignment step, totally makes sense. And it's the kind of thing where I think so I'm starting a professorship in the fall, and if I ended up with a student who was like really excited about the content of my thesis and was like, what should I do next? I would be like, this is definitely the correct thing to do next. And actually, just like one other quick side note is, if there's this figure in my thesis where basically I show the histograms of the distances between matched and aligned vectors, like things that should be close together, and matched and aligned vectors that shouldn't be. And when you're doing feature learning for like metric learning, basically, you want those histograms to overlap as little as possible. And if you don't do the binarization step and you just train the model to output continuously valued features, the distributions are much better separated. So like, there's no doubt in my mind that alignment would work better, not only for matching, but also for the final fine-grained alignment if you learned the feature representation and the alignment procedure end to end. So yeah, this is one of those things where like I drilled super hard down on this problem and like really, really cranked on it. And as far as I know, no one has picked up this thread of research since then.
Yeah, I see. Well, anyone listening to this podcast, I'm sure you'll have plenty of people interested in this problem now. So.
Yeah, I mean, it's funny, like, people say that when doing your PhD, you become like like the world's leading expert in like a sub field. And so there was like a short period of time, and this might still be true, where I was like the world's leading expert in like matching and aligning MIDI and audio files with neural networks in the loop. And there's so many like MIDI and like music information retrieval and like neural network and like matching, aligning, all this stuff that like makes me in this tiny constrained domain. And as far as I know, there's no one else working in that domain these days.
I see. Yeah, and then so I guess the end kind of output was this MIDI dataset. So do you think that nowadays this would be like maybe people would be interested in hearing about what's in that data set and what it might be useful for?
Yeah. So, like I said, what I had really hoped would happen was that I produced this big collection of ground truth transcriptions of music audio files, and that we could just, train a big CompNet or whatever to do music transcription and solve the music transcription problem. And to be totally honest, the data set is just like a little too noisy for that, because sometimes
Mm.
the matching goes wrong, and sometimes it doesn't align it perfectly, and it also is it's kind of invariant to some things that you really care about. Like, for example, if I have a transcription of a song, but there's no transcription of the vocal track, for example, then it'll totally work fine, and it'll just say like, oh yeah, this is a perfect transcription. And you don't want that in your ground truth. It's a little noisy and messy. And so it's no one has actually tried to train a transcription system based on this data. I imagine you could do it and it would work, especially if you then like fine tuned it on a cleaner data set. Um, but yeah, as far as I know, no one has really tried that. What people have done a lot with this data set is that I think it's the first time that someone just kind of said, hey everyone, here's a bunch of MIDI files. And so a lot of people who like if you want to train a generative model of MIDI, then there's a zip file online that you just download and it has a bunch of MIDI files in it and you can train your model on it. And that I think is like probably 90+% of the use cases of this data set at this point.
Mm-hmm. I see. Well, yeah, so I wanted to save some time to talk about things that you've worked on since the PhD,
Sure, yeah.
if it's okay.
Yeah.
Yeah, at least from my perspective, it's impressive the number of different areas you've gone into. So we talked about like the music VAE, but then also GANs, transfer learning, and now semi-supervised learning.
Mm-hmm.
So do you see some path connecting what you worked on in your PhD with these, or is it kind of just you wanted to explore new areas?
Yeah. So I mean, like a good trick to be able to do when you're like a researcher is to look back on the past however many years of your research and pretend like you had like a very specific goal in mind, especially if you're applying for faculty positions, because you really have to like make a coherent story. And I would say, yeah, I mean, a lot of it was exploration because by the time I finished my PhD, I knew some stuff about machine learning, but like I said, it was all stuff that I sort of learned ad hoc. And there were a bunch of things that I just, like, I had never trained a model on like images, for example, or text for that matter. It was like all spectrograms. And and I basically never trained an RNN because I couldn't really like afford to. And so there was a bunch of stuff that I wanted to learn and some sub problems that I thought were important. But I would say like if I really had to if I had to say like define a path, what probably happened was that especially right when I was finishing my PhD, everyone was excited about deep learning, or most people were, but everyone was criticizing these models because they required a lot of labeled training data to get working. That was kind of the recipe. It was like label a bunch of data and then train your model with supervised learning with SGD, and it works great. And if you don't have a ton of labeled data, then like maybe you're out of luck. And so that kind of motivates work in unsupervised learning, in semi-supervised learning, and in transfer learning. And those are the things that I ended up working on because, again, like to me, it's helpful to motivate research based on real world problems. And if you have a bunch of people who say, hey, this stuff seems really cool and I want to apply it to my problem, but I just don't have enough labeled training data and I can't afford to get more, then I want to help those people. And, some of the GAN stuff is unsupervised learning. It might not be the most helpful in that direction just because most people don't use GANs for like representation learning, for example, and they don't work as well as other methods for semi-supervised learning. But certainly like our line of work on semi-supervised learning, which first we had this paper on evaluation and then we did mix match, remix match, and fix match, is motivated by that. And then really like the T5 paper on transfer learning for NLP was really a reflection of the fact that it started to become true that there was this nice recipe for natural language processing that allowed you to really use a lot less labeled data. And I just wanted to like really drill into that problem.
Yeah, so if there's a connection, it's that in this music domain, there's probably very limited funding you mentioned, but also just limited data to work with. So
Yeah.
these types of methods could potentially go back and help in that domain.
Yeah, 100%. And I haven't really made that
Yeah.
connection back at this point, but totally. I mean, I was just very used to like the data scarcity problem coming through my PhD.
hmm Yeah, then I just had a more general question about T5. One thing that really came across as I was reading that paper, and I guess one of the big contributions is that you came up with this kind of unified interface
Mm-hmm.
of text to text. And then it seems like throughout the paper, you were trying all of these different like alternatives, like alternative training objectives and things like this.
Mm-hmm.
And somehow like the simplest one kept winning out. And so in the end, it was like really satisfying. So
Yeah.
do you think there's something fundamental there that kind of ultimately simplicity is like a key property that we need to strive for?
Yeah, I really feel that that's true, and this is one of those things that like I think if you stopped most researchers or practitioners and you said is like a simpler or more complicated method better, they would say like, oh, it's a simpler method. Assuming they work as well as each other, like is the simpler method with fewer hyperparameters, fewer things to turn better than the complicated one? They would all say the simpler method is better. But somehow there's this like anonymous group of reviewers and who don't believe that. They all hate simplicity. We had the series of semi-supervised learning papers: mix match, remix match, and fix match. And mix match and fix and remix match, the first two, got in on their first submission, no problem. Like not like, outstanding reviews, but like we never like they were just solid reviews, got in. Fix match has been now rejected twice, and it is the simplest and most useful and best performing of the three methods. And I'm not one to like read into like small sample sizes, but I just feel like there's like simplicity in machine learning algorithms is just so important. And if you can simplify your method more and it works as well, you should always do that. And to me, that's a major component of the text-to-text framework. It's always the same objective. It's always the same learning rate, the same optimizer. It
Mm-hmm.
like all you have to do is cast your problem in this format, which in my opinion, most NLP problems that deal with text can be. And then that's done. The recipe is over. Like there have been BERT, which is a totally amazing achievement. There have been many papers which are like kind of like how to fine tune BERT. And with T5, if you believe me at least, you can't write a how to fine tune T5 paper because it's all the same problem. It's all text in, text out. It's all teacher forcing. It's all maximum likelihood, same optimizer, same objective. And that's a really big deal to me personally.
Yeah. I mean, the results in that paper are obviously very impressive. And then I saw this other paper where you basically show that it's learned a sufficient amount of knowledge to do question answering.
Yeah.
But I guess as researchers, we move past the positive results quickly and ask, like, what do you think are the limits to this paradigm,
Yeah.
or maybe to T5 specifically?
I think a good like preliminary answer, or like at least we get one additional step towards that answer now that the GPT-3 paper is out, because they tried things at a bigger scale than we did and attacked some of the same problems. They used a different learning paradigm in the sense that in my opinion, they're basically doing very large scale weakly supervised multitask learning, and we're doing like what is roughly unsupervised pre-training followed by fine-tuning. And but the point is that they show that when you make the thing bigger, it learns more facts. And I don't think we have a rigorous understanding of this, and trying to get a better understanding would be a very important line of research to me. But it does really seem that as you make these models bigger and you train them with the unsupervised objectives that we use, whether it's language modeling or mass language modeling, they just pick up more skills and more knowledge and more facts that are very easy to get out of the model with natural language queries. And that's sort of what I mean by weak supervision. It doesn't have to be exactly formatted in the perfect supervised task format. but it does tend to associate these concepts in a super useful way with a really, really simple and cheap in terms of annotation pre-training procedure. And I don't know what the limits are. I think there was actually a nice paper that came out after T5 by Rowan Zellers from University of Washington. It's a new benchmark that the goal is, it's sort of a question answering a benchmark, but the goal is basically to take posts from the Reddit advice subreddit. So, and these are complicated questions, like legal questions, and answer them. And the answers are multi-paragraph answers, and they have to be factually correct. And that, like, sure, that would be a very, very useful machine learning system, or just an automated system if we were able to do that. But the models that we have, they don't always generate factually correct things. Depending on the approach, you don't actually know where the knowledge came from. And they often have trouble, generating really coherent long answers or long pieces of text. And so that kind of encapsulates a number of the current limitations of this approach. But I think for like a lot of the problems that at least people were thinking were difficult last year, like the Winograd Schema Challenge, for example, or even just like trivia question answering, I think that we will probably be able to, we already have and or will be able to sufficiently solve those problems with scale if we wanted to. Not that that's the most satisfying way to solve these problems, but yeah.
Yeah, that's an interesting answer. I guess moving to this other stream of work, like you mentioned with mix match and remix match, could you maybe just describe like what the goal of that type of work is?
Yeah. So that, the like retrospective way that work came about was that Avi Tal, who's the first author on the realistic semi-supervised learning evaluation paper, he started his residency. He was a friend of mine, and he basically said, semi-supervised learning seems like it's a good match for many real-world problems. Like there's many people with a lot of unlabeled data, and they've only labeled a little bit of it, but it doesn't seem to work well enough. Let's like try to make it work really well. Like let's get it working on ImageNet. And as we were working on this problem, we kind of realized that the evaluation procedures people were using were not consistent, and there were a lot of ways that people were saying that these algorithms were useful without like them actually being useful in that way in the real world, if that makes sense. And so we wrote this paper basically saying, the way that you're evaluating these algorithms is not realistic. And we didn't actually make any progress on semi-supervised learning. And then maybe less than a year later, one of my colleagues, David Berthelot, who is incredible. He has like a golden touch for machine learning algorithms. If he writes it, it like will just work, and if someone else writes it, it won't. He's amazing, and he came to us and he said, "Hey, I kind of was thinking the other night about semi-supervised learning, and I wrote this algorithm, and it works really well on your benchmark." And we were super skeptical, and we all like scrutinized his code, and it did work super well. And that was mix match, and then we've sort of just been making it better since. And the goal with mix match and that series of work in particular was basically to make these semi-supervised learning algorithms work with as little labeled data as possible. And in the most recent paper, Fix Match, we actually have results for where you have one labeled image per class, which is kind of like one-shot learning. It's not exactly the same, but the point is that we just want to make it as cheap as possible for people. Like if I have a big unlabeled collection of data and it's expensive to label, I want to let you label as few as possible and still get good performance. And of course, we're applying this to CFAR10 and SVHN and ImageNet, so it's not applicable to every possible domain yet. But I think we made a lot of progress on the extremely limited data regime for semi-supervised learning.
Yeah, again, I think you had this one result where it was something with, I think, like 200 training examples. You were able to still beat the state of the art or something like that.
Yeah. We've done this thing a couple of times now where we've said like the performance of our algorithm is the same with 10 times fewer examples. And one of the reasons that semi-supervised learning is fun to work on is that, in supervised learning, you're always just trying to make the accuracy go up on the whatever training set you are. So if you want to get state of the art, you have to just beat the last person's number. But with semi-supervised learning, there's two axes. There's the number of labeled examples and there's the accuracy. So if you can either say with the same number of labeled examples we do better, or you can say with fewer labeled examples we do the same. And because you can push in these two directions, it's a little more of like a rich field as far as like setting competitive results and stuff.
I see. Yeah. So these are some recent things you've been working on, but like, so you're going to be starting at UNC as a professor. Do you have like visions for the lab you want to build or things that you want to work on?
Yeah, totally. I want to continue working on learning from limited data, so transfer learning, semi-supervised learning, etc. And one thing that I expect to shift a little bit is that when I go back to academia, there will be more people who want to use machine learning who aren't sort of super technical people, like let's say at the medical school, and whenever someone who doesn't work on machine learning has a problem where they think machine learning might help, like the vast majority of the time, they don't have a bunch of labeled examples. So if they come to you and say, oh, I only have 100 labeled examples and I have a bunch of unlabeled data, if you just say, oh, I can't help you, that's a drag. But if you can say, oh, I actually work on that kind of problem, let's see if we can apply some of the algorithms to your domain, and hopefully I'll get some fruitful collaborations that way. Answering some of these more philosophical questions around like, why does this work? And can we be more rigorous about, for example, why the transfer learning for NLP recipe works and when it does and when it doesn't? So these are questions that you can answer without, a ton of TPUs. Those are also the kind of questions that I'd be excited about working on at UNC. And then I guess the other direction that I'm really excited about like today is I do think that the exciting thing about the closed book question answering results that we talked about, where you're kind of extracting knowledge from T5 by asking it questions, that's an exciting line of research to me because it works really well. There are some outstanding issues with it, like I mentioned, you don't know when things are factually correct, etc. And not that many people are working on it. So if you have something that is promising, that is not overloaded with tons of people working on the same thing, because I don't think everyone thinks of it the same way I do, and that has like a number of outstanding issues, then you can really crank down and write some interesting papers, I think, without getting scooped, for example.
So you said the factual correctness is one issue.
Yeah, factual correctness is one issue. Another issue is that the model that works really well has 11 billion parameters, and people don't want to deploy models with 11 billion parameters. It's hard. If you have a big language model that got all of its knowledge from masked language modeling, we don't know how to train the model to remember or forget a specific fact. If it answers a question incorrectly, I can't go in like I can with a knowledge base and edit that fact. And some other methods that have been coming out recently, like Realm and RAG, deal with this problem by basically allowing the model to retrieve a specific document. And our approach doesn't do that. But to me, that's exciting because it means that we can develop methods to help our thing do that. And maybe it'll work even better. Who knows?
Yeah, it definitely sounds like a fascinating line of research. And that's really good points about applications. So like in the medical domain, I think people probably underestimate the amount of data that's needed to get a lot of machine learning models to work. So these types of methods are really applicable there.
Totally.
Yeah. So I guess maybe to end, if you could come up with some grand summary of advice to maybe someone, maybe an undergrad getting started in the field that might eventually apply to UNC.
Yeah. There's so many random pieces of advice. But I would say that in particular for people who are doing your PhDs, it's very normal and it's very okay if you flounder around for like a year or two. I think that's a very common experience, and it can feel really difficult at the time, and it can make you question like what am I even doing here? But it's super common, and it's what like the hope and what you should be striving for is to find a problem that you can chew on for like 3 or 4 years. And if that doesn't happen for a year or two, then don't be hard on yourself. And a lot of PhD advisors, mine included, who was an amazing PhD advisor, and I really love him, but a lot of them aren't going to spoon feed you a problem that you can work on for 5 years. And so it can be really disheartening at the beginning to be like, what should I even work on? But finding a problem that allows you to write a couple of papers about it and allows you to learn a lot is not easy but important. So that's what I would suggest people try to focus on.
Mm-hmm. Yeah, well, thanks for going back. This was fun.
Yeah.
Getting to talk about what you worked on before and how it connects with things that you work on today. So
yeah, like I said, this is a super fun interview to do because people usually don't ask you about your thesis, but it's such a it's a labor of love, and so it's really fun to like think back on it and reminisce a bit. So thanks a lot for talking.